So, welcome to this 11th lecture of MCS 507, a course on mathematical, statistical, and scientific software. So, the purpose of today is to consider parallel computing, or at least high level parallel computing, um, mainly an introduction on the tools that Julia offers to um, program parallel computers. So, um, Julia uh, generates code. So, and there are several stages. So, in one sense, Julia is a very high level programming uh, language. Um, so there is types that are inferred, so the user can provide types, but they can also be deduced. Um, there is the Julia compiler, and then there is the code that is optimized and compiled to the native code. So the first time one often calls Julia program, just like a scripting language, Julia, and then the name of the program at the command prompt, then often it takes a while, and that could give a very negative impression that Julia is actually slower than a scripting language, Python. But it's the second time when the function is called that the native code, the optimized code, is then actually called. One often does sometimes a call to a function with a small input to do the compilation, and then separately one does the timing of the second call, then on the larger input. Okay, so just to illustrate how you as a user can see this, the code that is generated, let's look at this very generic function. Julia is really short in defining functions. So you notice here that the function 4 times x, so the star operator can even be omitted here. So there is no typing provided by the user in the definition of this function. So the function is thus generic, so it can just work with any different data types. We can specify the code that should be generated for a specific type. So here is the code, the bytecode that is generated for the low-level virtual machine for the 64-bit floating types. So the main point is not the code, although you might be recognize the 4 times x and then the minus 3, and this is already pretty low level. It can even get lower than that, and it's most likely that the formatting here is a bit mangled up, but you can essentially also ask for the native code, the generated assembly code for one particular type. So here again, the 64-bit floating point type. So this to kind of illustrate, to introduce the low level and the high level view on code. When we talk about parallel computations, we distinguish between 3 fundamental types of parallel computing. We have the computers connected in a network together. One can still use this in one single computer, uh, even though the memory is then shared by all the processors. But typically in that model of computation, one considers distributed memory modules. So to go from one memory module to another memory module, one needs the intervention of the processor managing that particular memory module. So picture here would be quite useful. So in the second type of parallel computing, there can still be several memory modules, but essentially all the processors, they have direct access. So if there are separate memory modules, then the processors can independently access all the memory modules without having to rely on another processor. So this is typically the multi-core processor. Every processor is typically now a multi-core processor. The third type of parallel computation is acceleration with graphics processing units, or GPU computing. I will only mention this. Later in the course, we may actually get to specific packages that can exploit GPU computing, but this topic is still a little bit too technical for a general purpose software course. Although the best way of essentially doing parallel computing is to call libraries that are optimized and libraries that work with the hardware that is there to make it go faster. Okay, message passing. Message passing is a standard. Some people find it inconvenient to use. And there are definitely better ways to do message passing. Message passing can also be done in Python. So next week is entirely devoted to parallel computing, and we will be introducing the message passing interface. Some people find the message passing interface an outdated standard, but it is a standard and it's still worthwhile to consider. So there is Julia and MPI with coding examples. So this reference might be a little bit dated now, but in short, how do distributed memory processors communicate with each other? They communicate with each other by passing messages. Then there is GPU acceleration. Here is another reference. So the nice thing about the low-level virtual machine compiler is that it can target both CPUs and GPUs. This is here a reference that seems specific for CUDA. CUDA is the Compute Unified Device Architecture of NVIDIA. But an advantage of the high-level GPU acceleration is also that that there are different packages out there that can target any general GPU. And again, if you call predefined libraries, then it's mainly up to you as the user to tune certain parameters. So how many processors do you want to use for GPUs? How many blocks do you want to launch? How many threads per block? But then the actual running, the actual compilation isn't also hidden for you. So that's another advantage. Okay, in this lecture I will mainly illustrate the working with the package distributed. and how to use threads on some very, very simple examples. In the last part, I will indicate how the BLAS library is already optimized for multi-threading and how that can be called from within a Julia session. So this is parallel computing with Julia, but the lecture could also called interactive parallel computing. So supercomputing and high performance computing is often far from being interactive. It's mostly the jobs that have to be scheduled in batch, and with a supercomputer, one tries to optimize the usage of the computer. And that often is at sacrificing the convenience and the time of the user. Here we assume that we, as users, have the entire computer at our disposal. So these are interactive sessions. Okay, when we think about distributed computing, we think about one manager and several workers. So when we launch Julia with multiple processes and we are using the distributed package, I think that is standard, part of the standard library. Then we can query the number of processes, which is one more. So in a way, there is the master process, the process that we always have when we start a Julia session, and then there are four extra processes that are created. Now, what is a process? A process is an independent, can be viewed as an independent program. So on a computer, there are many, many programs running. Every program has its own code, its own space where it stores and locates its variables. So a process here is synonymous with a program. So in a distributed memory environment, the processes are working independently from each other and they each have their own workspace separate from each other. Okay, so typically the communication overhead is important and we run on distributed memory computers, jobs that are actually very well scaled, so that require very little communication overhead. So the Monte Carlo estimation of is actually one of the or any simulation is actually any um, is very suitable to simulate here a very computationally intensive computation that can run independently on many different executed by many different processes. So the ideal parallel computation will start up a number of processes, let them run independently, and then collect the result afterwards. So here is the Monte Carlo simulation. Monte Carlo simulation can be viewed as throwing darts and count every dart that lands as a success and then average the number of successes versus the total number of trials. So here in this simple loop, we generate two random numbers in between 0 and 1. So we are estimating the area of the first quadrant in the unit circle. So the count here counts the distance from the unit circle, from the origin. If that distance is less than 1, so it's the distance squared, but if you take the square root, it's the same. If the squares of the components of the two random numbers is less than 1, then you are in the first quadrant and you count this as a success. So the ratio of the first quadrant of enclosed by the unit circle and the square with area 1, that ratio tends to be, so if we do the simulation here, but if we have the actual area, then that ratio is pi over 4. That's why we multiply here by 4. So this is a long explication to set up the computational experiment. So we estimate pi. It's a very bad way to estimate pi that way, by the way, but we do have a computationally intensive computation. So we do 10 billion function evaluations here, or 10 billion random trials. So this is done in a script. So in a way, this is good to time code. So in the last time we ended with timing, or in the first week, in the first lecture of this week, in lecture 9, I compared C, Python, and Julia. I didn't really say how to time, but here is one way how to time one particular function in Julia with time. And that will measure the time in seconds. Okay, so how do we make it run faster in a distributed version? So the purpose of this lecture is to indicate what kind of tools that we have, and how can we make this run in parallel as quickly as possible. So next week I will say something about message passing. Here is certainly, if you do this on one single computer, then running this with many different processes is quite simple. You say that you add the I think decorator I can use. You add the directive everywhere to it. It looks like a directive. So you have to decorate your function. So it's also called sometimes a decorator, but it's a macro as well. So the point is that you see to use it, you don't really need to know what it really means. So you make this function available for distributed execution. So what often happens with parallel programs executed by memory by many processes is that every process will execute the same code. So we will have still one script, one program, I should say. So here I said it, the script. So when I wrote this, I was still thinking about scripting languages. So I have a number of workers. So we illustrated function number of workers. There is now one parallel program, and the parallel program is defined in one line. So we will map the function that we decorated with everywhere, but it's still the same function from our sequential run. So that's also the cool thing, because when programs are running in parallel, the order of execution changes, and if you have to recode things, then some difficult issues are happening with the correctness. So how can you still be sure that when you compute something a lot faster, that it's still as correct as the sequential version? So you may end up with a faster program, but that's actually not always, that has bugs in there. So that's actually a non-trivial problem that with shorter code, with clean code, where you, as much as possible, you recycle the definitions of the original functions, that actually is preserved. So here, what is the whole point again? The mean is part of the standard library, the statistics. So I was also using not only distributed, but I was using statistics. So this is where the mean comes from. The PMAP and the N workers, that all comes from the distributed module. So this program will execute the parallel pi, and it will be the master process that will execute this. When I run this with 4 workers, the main thread or the main process will, as they say in Unix terminology, will fork 4 worker processes. And we will do the timing in exactly the same way as before. So we do the timing. Okay, let's do this at the command prompt. So at the command prompt, I'm also doing the time. A time that I like is the wall clock time. So that's the actual elapsed time. So we do the time for the one-threaded computation. So here you see that the wall clock time takes 2 minutes and 2 seconds, and that is corresponding to the elapsed time. So the elapsed time is what time the internal program indicates to us. Well, there's nothing much happening. So there's no data movement. We have no internal large data structures. This is a very computational intensive process. So if you have memorized the digits of pi, you see the 3.1415, but it's not going much beyond that. So with our 10 billion function evaluations, I don't think we have much more correct than 4 or 5 decimal places, if you like. Here is the distributed version with 2 processes. So the total number of processes is 3. So I hope that I can make this run twice as faster. So I have 3 processes, but even if you would have only 2 cores on your computer, it would still be worthwhile to do this, because the main process that forked the 2 workers will be sleeping, and it will be your 2 core computer will be busy running those 2 worker processes. So now you see I go from 2 minutes and 2 seconds to 1 minute and 20 seconds. Wall clock time. The elapsed time is 77 seconds. So the wall clock time gives me 80. The CPU time is 77 seconds. Note that the user time is 2 minutes and 37 seconds. So user time means the total CPU time. So your computer has actually worked a lot harder. But the real time, and that's the wall clock time, that's the time that was elapsed during the beginning of the time when we launched the process and the ending, is actually 1 minute and 20 seconds. So you also see that the system time, which was negligible here, less than a second, then here it becomes 2 seconds. So the system, the operating system, also needed to be involved in this experiment. Okay, so this is a run on multi-processes. So you can see I did this on a 44 core machine, and I could kept on doubling the number of processes. And you see that the time, as time goes on, I get still good speed ups. Still, the speed ups are actually not computed here, but you see it goes actually quite well up till 32, from 32 to 64, that I don't have too much gain anymore. So there is also a big leap here between 42 and 43. So, but this has to do with the number of cores that I have. So in doing multiple processing, then what you actually want is you want to map the number of cores you have to the number of processes. So if you run too many, so then this will show. So that's why we have the 42 and the 43. That is so it actually with 43 it tends to go slower. So okay, so distributed memory parallelism. So there are two primitives here. So we have remote calls and remote references. Julia provides distributed array data structures, which we have not exploited here, but we have seen the PMAP implementation. So the PMAP maps functions that can run everywhere and is a very, very powerful mechanism for ideal parallelism. Okay, so that was a very, very brief introduction to distributed computing. So then there is the multi-threading, and that might even be shorter. Although short is good here. So you can see that already with ideal parallel computation. So we will do a little bit on MPI, and you will see that with MPI there's actually much more involved there. Okay, multi-threading is different from multiprocessing in the sense that every thread has access to the main memory, has access to the same memory module. This makes multi-threading much more powerful and therefore also much easier to get good results with in terms of observing speed up. But also at the same time, it's much more subtle. So one has to be a little bit more careful as a programmer. We will do here again interactive parallel computing. So at the command prompt, we can indicate how many threads the interpreter may use. So here I launched this with an environment variable, so the number of threads. So here the number of threads matches the number of that I just indicated, although there is still one main thread that is running here. It just isn't listed with the end threads. Okay, so every thread has an identification number. Here we have a parallel for loop. So with the acrawl 3 threads, we indicate that we are going to run a loop that is executed by every thread. So it is a loop, but then the loop is not like one thread executes a sequence of commands. No, every thread does something. Every thread executes the statement, print statement. And you see that they execute out of order. So actually the first thread prints last. But that could also be that it might be when you are executing this, it may be different. It may also be a coincidence that this happens this way. But this is the indication that it did run in parallel. Okay, we can have threads writing into a shared array. So this is now one mechanism how threads can share information and how they can report information back to the main thread. So here the output is A. So the output, what every thread does, is just giving their thread idea. But instead of having the thread idea, we could have a function that every thread executes. And that will be again the mechanism for the high level parallelism when we estimate pi, but now with multiple threads. So here it so happened that the writing to the array was somehow synchronized. So even though the threads were executing at any way they wanted, so the array ended up neatly sorted. Okay, we have our multi-threaded Monte Carlo. So what I did here, I built my own random number generator because there might be the many, so that when a random number generates a random number, it has a state. So if many threads at the same time call the same function, they are going to change the state of the random number generator. If it is a very good implementation at what they call a thread safe computation, then the threads will be blocked from running their they will have to wait till other threads will have generated their random numbers. So again, there is a lot of stuff that can go wrong even at the highest level, and even with a simple call like calling a random number generator. The other thing I should have mentioned is that with Monte Carlo simulation, what you actually do not want is that all the processors generate the same sequence of random numbers. So I did not mention this in the distributed version. I'm actually kind of assuming that if every process starts running their own random number generator, that they generated different random sequences. So here you see this happening. The first random number, or the random number generator, starts from some random seed. And as a seed, I take the thread identification number. So this is a function that will run using the threads, but it will run with, so the code here is now actually changed. And most likely one has to be careful when one runs multi-threaded applications. One has to be careful for potential conflicts. Okay, it gets a little bit more more complicated. So we now work with very large integer numbers, and the integer numbers, they are 32-bit numbers. So you see the modulo 2 to the power 31 here. So they are scaled to fit within the 0-1 range. But other than that, the short function is actually changed at the random number generator. So Monte Carlo for multiprocessing, generating very reliably and very non-repetitive sequences of random numbers is something that is important. So, and perhaps this is also, of course, in statistical computing. Perhaps we could address this at some point. But you see, these are ideal parallel computations, but there are issues that one has to be aware of. Okay, so now we run our parallel loop, and the parallel loop is now that every thread calls the function estimate pi. And we still are running this with 10 billion numbers in total, but the number of threads is a divisor in this 10 billion. So if we have 8 threads, then there will be 10 billion divided by 8 samples generated. So thus we may hope for a speed up of 8 if we run this with 8 threads, provided that our processor has sufficiently many cores. And here with multi-threading, most modern processors support what is called hyper-threading. So even if you have 2 cores, it may be best to run with 4 threads. So the cores can handle, typically each core can handle 2 kernel threads. Okay, we again use the statistics package, the mean. So we print the estimate for pi. Okay, so the multi-threaded version. Again, I do this with the wall clock time, but there is also the internal time, the CPU time. You see that the wall clock time goes from 1 minute and 2 seconds to half a second. So this is quite a good speed up. And by the way, this is actually the same algorithm that we ran before, but then it could be that it is under a different computer. I might not have been so consistent here, but it would not surprise me if the multi-threaded version would be in generally more efficient, because you don't have the multi-processors that are being launched, so the several processors. So threads are often called lightweight processors. There's also the communication overhead even at the end here, that would be lighter. So in any way, you see the system time. So the system time is actually the same with 2 threads. So it's still less than a second. So there's a lot less overhead with a multi-threading. So that's also the main point here. So this was still done on the same workstation. But here I was a little bit more frugal with the number of processors, and actually you see that the speedups go actually quite good. So we get from 1 minute to 10 seconds. Now the point is also that as far as it gets to 10 seconds, the computation itself is not so how would I say this? So the computation gets too small for it to benefit for parallel computing. But still, one the multi-threading is definitely very promising. And we did not have to do a lot of effort. Okay, so here is now the last issue. So the best way to do multi-threading is to use a library where the multi-threading is already supported. So I will end with the illustration of the BLAS. So we can multiplying matrices together is a very, very basic operation. So there's a lot of effort that has been spent to make this run much more efficiently. Here we have the matrix multiplication, where we do this in place. So we declare a similar matrix to B, and then we do the multiplication, the in-place multiplication of A with B. So you can see when we have the first row 1 2 multiplied with the first column, so the matrix B is now 1 1 1 1 1, we get 3 at the first row, so you can verify that this construction is correct. So we have the in-place matrix multiplication, and we are going to use the basic linear algebra subroutines package, BLAS. So this is highly optimized. So we can define the number of threads in a program that BLAS must use. So if our application, the main bottleneck is matrix multiplication, then everywhere where we do a matrix multiplication, it will be optimized. It will be running not only the optimized code, but it will be running the multi-threaded version. Okay, so here is the in-place multiplication. So we are generating random matrices. The dimension can be provided on the input, or actually should be provided. So here you see the capturing of the arguments. So args is predefined. If there are too few arguments, then you write an error message. Otherwise, you parse the command line arguments, which are in general strings. You parse them, so the number of processes, the dimension n, and then the number of threads. Okay, and here the rest of the code goes. So this is essentially a benchmarking program. But again, to indicate that you have to do this on sufficiently large matrices. So here I did this on matrices of size 8,000. So multiplying two random matrices with of dimension 8,000 with one thread takes 20 seconds. If you can use 32 threads, then this has dropped to less than 2 seconds. So this is one factor less on an operation that is actually quite computationally intensive, but at the same time very useful. So time also gives us with other metrics, provides us with other metrics. Okay, so this was a first introduction. The BLAS example also provides me an opportunity to talk about performance. So you can check on your computer how performant your computer is. So there is the flops. Flop stands for floating point operations per second, and you can check the peak floating point performance that is computed using the matrix operations provided by the BLAS operation. I forgot now what the GEMM stands for, but it's one of the operations that is provided by BLAS. So the point here is that also you have to pick your dimensions carefully. So you shouldn't do this for 10. So these are too small operations. And you see that the performance goes up. So this should be related to the clock speed, which is typically now measured in gigahertz. So modern processors do a couple of gigahertz of operations. Now the 10 to the power 11 here, this is a number with 10 zeros, or actually 11 zeros. And if you remember the billions, so the billions had also 11 zeros there. So with the peak performance, you get to 3 billion floating point operations per second. So, nice thing, you can actually immediately check this in a Julia section with the built-in linear algebra module. Again, we are closing our first week of introduction into Julia. This is another indication that Julia is oriented towards performance. Okay, I will conclude with one reference. There might be many. Are certainly many more. So this might be also a little bit dated by now. Um, and some exercises. For example, the quality up is an interesting comparison. So also, I indicated I was not very careful with the seeds. So if you generate multiple processors and you call a random number generator, verify that all the processors are actually giving you a different random number, even if they are executing this only once. So verify this. So there is the quality up. So if we ran the multi-threaded Monte Carlo and we divide it by the number of threads, instead you would keep the number of threads, but you would actually check how much more accurate is your result. So you can do this with the distributed version and for the multi-threaded version. So I hope that this was a very, very brief and very incomplete introduction to distributed computing and multi-threaded computing from within an interactive session with Julia on an ideal parallel computation, the Monte Carlo computation. I thank you for your attention.